I think we'll begin. Good morning, everybody. I wanted to start with this informal beginning before Merwin speaks. There's a very interesting collaboration that's emerging between the California Institute for Energy and the Environment, the director of whom is Carl, sitting right here, a large number of people at Lawrence Berkeley Labs, led by Ashok Goyal and Arun Majumdar, a number of colleagues from the California Energy Commission, ably represented by Ron and Gaiman, who of course works also at the California Energy Commission, the California Institute for Energy and the Environment. Whoa, too many acronyms here. And then CITRIS has been working on a number of energy-related topics for many years, again, mostly led by Ron and others from the California Energy Commission in areas like demand response and energy efficiency. More recently, Professor Katz and Ken Lotzus here, working with also Professor Sanders, the three of them are sitting together there, have taken a renewed interest in how internet protocols can be used in realigning the grid to accept renewables. Just last week, Gary Baldwin led a really great visit by the Vestas wind energy company, who are also interested in sort of macro-scale integration of wind into the grid. So a bit like our old sherry hours, there's just been this bubbling up of many aspects of how information technology can improve the energy problem, talking very, very broadly. And as I look around this audience here, we have people like Professor Bozer and Professor Evans, who are sort of working on micro batteries and micro sensors, all the way up to people like Seth and Randy, who are working on the whole aspects of the integration work with the net. I look around, there's real engineers like Carl Brown that know how to do real things. And we have a wonderful group. And so, just again, a little informally, we were meeting at Stonehenge, right? We had with a lot of friends in the audience here. Stonehenge is just down the street from Carl's house. It's opposite Berkeley Bowl, if you know this place. And so we started having these breakfast meetings that were a little bit like the sherry hours that we had a year or so ago. And it was clear to me that from all those meetings that there's a real bubbling up in a grassroots way. And this has sort of led to the birth of this little informal energy seminar called i4Energy. We started out by calling it i4Energy, like, you know, being trendy, like an iPhone. And then we had all these other I's, like integration, intelligence, information, and innovation. And it got to 4. We couldn't think of a fifth one, so it ended up by being i4Energy. And if you're really hackneyed and you say i4Energy, it sounds like I'm for energy, which sounds totally corny. And I even backed off from that for a while, but Carl bullied me into staying with the i4Energy thing. Sorry to be informal as I start this off, but it is Christmas. I can take a few liberties. And I think what we need to do next semester is all amongst ourselves as a group of friends figure out how we can rebirth the sherry hour, or maybe have an informal lunch like this every couple of weeks. And I know that Gaiman has been tasked by Carl to put that together. So if you have some ideas, Gaiman is the source of where the new talks will come from. That was a very long introduction to Merwin. I'm very sorry to take that from you. But as you can see from the title of this talk, it seemed like there's a large number of us that are interested in the way in which these new transmission technologies for renewable integration will take place. And actually, Merwin, that was one of the hottest things on the meeting that Gary organized with Vestas, where, you know, they have these wonderful wind farms, but unless we do the right thing with the kind of things that Merwin's going to talk about today, these will end up by being stranded assets, just like solar power in the remote desert would be a stranded asset. And I think there's something that this group can do as a voice in Sacramento even, to bring these developments together in a more flexible grid. So on behalf of many people in the room, there's almost too many people to name, but we wanted to thank Merwin for coming today. As you know, informally, there's a lunch afterwards that starts at 12, and so please stay for the lunch, get a free sandwich, stay as long as you like. Some more students will probably join us at 12, and I think that's the best way in which I can introduce. So a round of applause, I think, for Merwin. Thank you.
This is supposed to be on? Thank you.
Oh, you know you're being webcast.
Yeah, I knew that was the intent anyway, was to be webcast. Well, thank you for having me here today. And I'm not sure how you run these things, and maybe since this is the first one you don't either, I don't know.
This is a work in
But I do have about 30-some slides here that I plan to spend about 30 minutes on, so you can wait till the end to ask questions, or if you want, ask questions as we go along. This particular talk is broken into largely two sections. The one is that I want to set the stage by defining the research questions. What are the problems that we have to address? And then the second part is, since this was about information technology, I picked one particular technology suite that we've been looking at in our transmission research, technology research, that I thought I'd bring to your attention, that goes to the heart of what I think is information technology at the transmission level. So be known that there's a whole lot of other technologies I will not be talking about, and hopefully I picked the one that is of most value to you. So with that, I'll get started. The first thing I thought I'd get out of the way is a bit of an advertisement as to what was behind this particular presentation. My team, which I have, and two of them are in the room right now, Lloyd Saboka and Larry Miller, who came in to sit and listen and keep me honest. They know more about this stuff than I do. And I think some others are calling in, as a matter of fact, today. There is a team behind all of this that helps develop the research questions, identify the researchers. We work very closely with stakeholders of all kinds in this arena of the transmission community. And then we identify what kind of research needs to be done. And then we manage some of the research projects, which are all funded so far by the California Energy Commission through the Public Interest Energy Research Program, which is basically the ratepayers of California in the three IOUs, PG&E, Southern Cal, and San Diego Gas and Electric, who are funding this research. And this particular research here, or the program, this presentation, is based on a study that the team did, which was to answer the general question of what kind of new emerging technologies could improve the integration of renewables into transmission. As Professor Wright indicated, that Vestas indicated, it's actually a big challenge, much bigger than you might suspect. And we think technologies may help with that. So with that said, the purpose of the particular study was to link transmission with the renewable technologies, and we call this loosely integrating the renewable generation into the transmission system. And so our purpose was to determine these research needs, and the idea would be then this would be used, as a matter of fact it has already been used even when it was still in draft form, to form part of the i4, which is the state's integrated energy resource program, which lays out each year the general policy for the state, at least from the California Energy Commission, of what should be focused on to keep energy, so to speak, flowing into the state and through it. And so I have the usual disclaimer, which is, since this was funded by the California Energy Commission, this does not necessarily represent their views, and this presentation has not been approved or disapproved by the Commission, so I'm freelancing it, so to speak. But I want to give them credit for the fact they funded us to create most of the information that's in here. I'd like to start this presentation by talking about what I call the saga of renewables and transmission integration. It is a saga. It's actually a fairly complex process on both sides of the equation. And so I'm going to sort of tell this from the perspective of the new renewable power plant owner. And I picked wind as the poster child here because it's the one that tends to have the most problems. But renewable power plants in general on a spectrum will have different issues with integration into the transmission system, but wind catches most of them. And so what happens is that this new power plant owner, the first thing to do is he or she is smart. That may be my phone. But Larry, would you hold it for me, please? And so if they're smart, and so the first thing they want to do is they want to go to where there's the most renewable energy for the particular technology that they've picked. And so the wind goes where it's windy, solar goes where it's solar, the biomass goes where there's lots of leafy stuff. And so as a result, they're driven by where they're going to locate the plants more by the resource than by other considerations. So they go pick a windy site, and then the first thing they want to do is, since they're producing this electricity, they want to connect to the transmission system to get it to the customers in the urban areas like the Los Angeles Basin, the San Francisco Peninsula, and the Bay Area, the Central Valley. It's particularly around Sacramento, et cetera, et cetera. And the first thing we find is these plants are usually remote from the transmission system because people don't generally live where it's extra hot, extra windy. And so right away they have a problem. How do I get connected to that transmission line when there's quite a distance? So the first thing they're going to ask the transmission, I call it the community because there's a lot of different players involved in this. They ask, well, gee whiz, can you hook me up? So the question is, can you provide access? And so we generally have to end up building new transmission out to them, but it's tough to do. It generally doesn't take real well. They have to try over and over again to get permits, and finally, eventually, they do perhaps get them built.
Where do they get the permit from?
From a whole host of people or entities. That's the problem. And I'll be getting a little more into that in a moment. But it is one of the issues. There's no one-stop shop for getting a permit for these things. And it is generally the biggest issue is permitting. I'll get into this more later on. Right now I want to just set the stage for, frankly, the challenge. So the power plant owner gets hooked up, finally gets a transmission line built out to the new power plant and breathes a sigh of relief and says, oh, now I'm set. I can get my power to market. But wait a minute. The transmission operator comes back and says, well, no, we have a problem here. Your particular type of power plant has some unusual characteristics which we now have to accommodate. And one, our system wasn't built to do that. And two, our operators, this is all strange to them. And this frightens them. And it also raises the degree of uncertainty and therefore increases or decreases the potential reliability of the system. So we now have to figure out how we're going to accommodate your unusual behaviors. So we're going to solve that problem. So we finally solved that problem. And now the power plant owner breathes a sigh of relief, said, now I can get my power to market. And the next thing that happens is he finds out that, whoops, it's not that simple. The existing system now turns out is constrained. You can't put a lot of new power onto the existing system for a number of reasons. One of them is thermal limits, and I'll talk more about what that is if you don't know what it is in a moment. And then there's another kind that have to do with instability, in which there are deratings of the transmission system. And as a matter of fact, it's considerable in certain parts of the transmission system, thousands of megawatts in certain areas, in which, due to instabilities, they have to back off the amount of power that can flow through this system to maintain reliability. And so the next thing that has to be done is that the existing system has to increase its capacity in order to handle all this new generation and get it into the urban areas. And as you might suspect, as you get closer and closer to urban areas, it gets tougher and tougher, for example, to increase capacity by building new transmission or even reconfiguring the old transmission. And so this sort of lays out the problems that have to be solved before we can get renewable energy to the customer. And so one of the things I'll talk about each one of these in a little more detail now. One of them is, the first one is providing the transmission access to renewable power plants. If you look at what the prediction is of where our new renewable generation is coming from, and sort of divided into two categories, those that need transmission and those that don't need transmission because they happen to be located very close to the customers, it turns out, and this is just my estimate, it isn't a real accurate estimate, but it doesn't need to be to get the point across, is that the vast majority of it is expected to require transmission in order to get to the customers. And so this is a lot of new generation that's going to be required over the next 10, 15 years up to 2020 time period is the one we normally are talking about for a 33% penetration. So this is one of the first things that we have to consider, is that most of the new renewable generation will require transmission. Now, as I've mentioned already, these renewable power plants are usually located in remote locations far from customers in the electric grid. And if you look at, first of all, the western United States, we do have a number of different renewables scattered throughout the western United States, as indicated by this map here. But if you look closer to California even, again, if you were to study this, you'll find out that most of these renewable sites for wind, geothermal, solar, and biomass are outside the population centers, which are represented by the L for load. And you have to get that power into these constrained areas in order to be able to sell the electricity.
Sorry, what are the green areas?
The green areas kind of represent where the power flow is expected to go.
Oh, I see.
Question here?
Just moving the power seems to be not peculiar to these energy sources. If I build a steam turbine, I also need presumably some wires.
You're right. You're absolutely right. We would have to solve many of these problems whether it was renewables or not. Exactly. The other way to look at it, though, if you don't solve the problem, we can't meet the renewable portfolio standards with the current approach. So either way, we have to solve that problem. But you're very good observation. I'm glad you saw that. Because it turns out when we were working on this program, doing the transmission research before, a few years ago, even before the renewable goals had been set and were being gone after in a big way, we were still doing much the same research because we've got to solve the problem regardless of whether it's a natural gas-fired power plant. Renewables do bring some of these special problems, though, that I mentioned. And I'll show you what that all means. But I'm glad you got that out of the way. So in order to hook up these new power plants, the renewables in particular in the remote locations, we will need new transmission lines between these power plants and the existing transmission. Now, siting new transmission is an extremely complicated and lengthy process, and here are some of the reasons. One, there are multiple stakeholders involved in this process. Stakeholders are those who are going to build this thing, who are going to invest in it, going to own it, operate it, as well as those who benefit from the transmission system that go in, as well as those who pay, so to speak, a cost in terms of perhaps environmental consequences or even direct cost in terms of rates. And this is a big struggle on benefit cost allocation regarding siting of these plants. And as someone, you raised the question earlier about the designated authority. There's no single state designated authority. There are many different authorities who have to do this siting, and there are numerous jurisdictions and agencies involved because transmission, unlike a power plant, goes across boundary lines. And when you particularly get into interstate type transmission, it gets to be a really big mess. Imagine if we want to try and move wind power from Montana and Wyoming to California. Imagine what Nevada and Utah citizens are going to say. You want to build transmission lines across my state so that you can have power from Montana and Wyoming. Forget it. It's already happening right now between Arizona and California. It's the big transmission line has been refused because Arizona said, no, we don't want to ship our water, which really what it translates to in many cases, through the use of cooling towers power to California. And then there are environmental considerations, and especially the visual ones. Those are the ones that usually seem to stop transmission nowadays. It's just people don't like the looks of them out there. And then it's now taken, for siting a transmission project, it's taken many years longer than it takes to site the power plant. So right away you begin maybe to see a problem. If you can build the wind plant in 2 years, but it takes you 4, 5, 6 years to build the transmission system, right away we have a problem with economics and with also meeting the renewable portfolio standards. And it's not unusual for a large transmission system now to take up to 15 to 20 years to site, is what the history is starting to show. And some of these have become infinite. You can't site, the time is infinite because you can't site them at all. so far anyway. And so it's beginning to become an increasingly big problem, and more so. So we need to find ways to accelerate the siting of new transmission lines in order to meet the RPS. Now the second issue I wanted to talk about, which is specifically related to renewables, is the ability to accommodate unique renewable behaviors. And I've shown up here the sort of big four. There are other forms of renewable generation, but these are the ones that are expected to meet most of the needs in California for the foreseeable future. And these are the general behaviors that you have to worry about: the intermittency issue, inertia, and actually its lack of inertia, ramping problems, which I'll explain a little bit later on if that's not clear, and an oversupply problem. So to go through each one of these briefly, the first one, again, our poster child for this one is wind, although we've actually just begun, as we, the community, have just begun to look at concentrating solar, and it probably will also have some similar variations due to the fact it can use only the normal incident radiation, and any little, even moisture you can't see will cause a scatter, which disturbs the concentration, so you get these kind of behaviors for solar as well. Quite as bad. But this comes from CalISO and shows you actual data around the Tehachapi of what typical wind pattern profile power looks like over a period of time, and it's generally a mess. It's generally very difficult to predict, but science is moving ahead and attempting to improve wind and solar monitoring and forecasting. It's going to be extremely important to be able to forecast, and so this is a very rich research area. A lot of work has been done in Europe in particular, but also the United States has done some work in this area. And it's getting better all the time to be able to predict. It's pretty easy to predict a few minutes, even hours ahead. It gets pretty dicey to predict 24 hours ahead, but you would like to for market reasons to be able to predict the first.
I mean, like out on the coast, it's often windy at 4 o'clock in the afternoon. But this doesn't even show anything like that, as far as I can see.
No, it doesn't. No. And even in the plain states, where I think it's probably better than in California, they still have quite a bit of variation. And it's due to a whole bunch of stuff. I'm not an expert in this area, but I have set in some seminars on it. And it has to do with even local geography affects it, or not geography, geology. Mountains and valleys and things cause all kinds of variations of flows. Despite the fact higher up you may have fairly nice level flows.
I noticed they draw the y-axis to -100. Is that anticipating that there would be a negative supply? Does it even fit under the axis?
Yes and no. I have to think about that one for a minute. In a sense, I don't think they did that for a reason, but I am going to show you in a minute where there is an oversupply problem where indeed, CalISO says they have to pay people to take power, so you could think of it as negative. But no, it's not like a potential fusion plant where you have to stop and charge the tokamak. That's really a negative situation. This is not true in wind, really, in particularly modern wind.
I wonder what exactly the average means. Isn't it that we would like to add up all the different contributors, and that sum should be flat, and the average seems to be a lot flatter than all the wiggly lines I talked about.
Yeah. The average is what it's doing is telling you what type of power on average you can get out of that. That's true. But it's really a statistical number. It doesn't have much meaning when it comes to meeting loads.
So if one would add up all the wiggly lines, the result still would be extremely choppy and have basically fade. So I mean,
I think I agreed with what you just said. Yes, Carl.
I don't think you can add the lines because each one is a different day. I think the average is for a given hour over a month. What is the average value?
That's right.
So
what it is, it's effectively.
work here.
That's right. It's effectively, I think, in this case, and I need to study this particular graph more, I'm going to guess that it's going to be the effective capacity factor, which is about the right range, because it's in around the 30% range for wind in California is the average capacity factor. But that averages out, and you're right about, it would have to be averaged over a period of many days on at a given hour to get that average. So, well,
That's what you
yeah.
could yield from a wind plant if you had free storage.
That's, yeah, assuming it's 100% round trip on storage, yes. Yes. But,
But that storage would have to be a deal.
or perhaps,
That would be infinite.
Yeah, so.
yeah, that's right. It's been the holy grail of this industry to find the kind of storage that would allow you to do this kind of thing. And matter of fact, we'd like to be able to even shift it more than just daily. You'd like to be able to shift it over a monthly period if possible. And pumped hydro is about the only one that comes close to doing that right now. And the next one down is generally compressed air energy storage that generates a lot of interest. But storage, you'll see later, shows up over and over again. If you can solve that problem, you can solve if you can solve the technology problem and the economic problems of storage, you can solve a lot of these problems with these things. Some renewable generators have low or no inertia. And what that means is that the traditional thermal power plants exhibit inertia via their rotational mass in the turbine generators. And in a sense, it's in some ways it's not either good or bad, other than the fact this is what the system was designed for. It's what the operators are used to. So when a plant trips off, it doesn't immediately lose all the power necessarily. It tends to coast down, and the operators are used to that. But now we're getting new power plants that don't do that necessarily. But some renewables do exhibit this traditional inertia because they basically use a thermodynamic conversion cycle. And that would be the geothermal, the biomass that burn it and turn it into steam. And then some of the thermal solar plants, particularly those that do have thermal storage and also use in some cases a thermodynamic turbine, they do behave much like the old ones, the traditional plants, so they're nice from that point of view. But there is a group of wind and some solar that have low or no inertia. And these are some of the thermal systems that use, for example, Stirling engines, if they don't have storage, which so far most of them don't. They have a little inertia in them. The photovoltaics, which have almost zero inertia, and unless, again, they have storage. And then wind, which has a little bit of storage in the rotor, but it's fairly small. And this is, again, the issue here is the system wasn't designed for these kinds of plants. We're used to this inertia. And where there's getting to be quite a concern about this is actually in the local generation. All of the photovoltaic rooftops, for example, what kind of problems are they going to create with what is basically at the moment a load issue, because this is not seen as generation yet. Someday down the road we may meter it and dispatch it or use it like generation, put it in the market, etc. But at the moment it's really a negative load, and it's affecting the load behavior, and that's pretty important when it comes to planning and managing the system, to be able to predict load behavior. And there's concern now about what this lack of inertia is going to do. So the lack of inertia may amplify some transient instabilities, but since a lot of these, by the way, are solid-state inverters that are the ones that have low inertia or no inertia, there's actually the possibility, because they're fast-acting, you could reverse this and use them, perhaps, particularly if you had storage, to be able to fight some of these transients. But right now, that's not proven, and right now it's not really accepted by the operators. Carl?
Well, there's currently spinning reserve.
So, yes.
Which can handle well-behaved sources at least. Why wouldn't just increasing the amount of spinning reserve handle the transient there? And so you're sort of substituting that inertia for the lack of inertia in the solar or the wind.
Exactly. I'm going to get into that in a minute, but you're right. At the moment, that's the proposed solution as you build more thermal plants. But to give you a hint of what the problem is that you need most of these in the urban areas, because that's where the problem's going to be, and that's difficult to build new thermal plants in urban areas. And so there's part of the problem. So yeah, right now the proposed solution is to build more thermal plants.
But not more thermal plants necessarily, but convert more plants to be used for spinning reserve.
Well, you see,
Or is that
well, the problem is that the plants that are, I'm getting off base here a bit, but the plants that are in the urban areas are, one, a lot of them aren't meeting the air quality requirements, and two, a bunch of them are threatened to be shut down because they use once through cooling. If those plants get shut down, then frankly we're in deep trouble. And that is the current path that we're heading down. And there's also some other issues. Yes, you can handle them with spinning reserve, but there is an issue in that we have to be able to, the whole WECC has to be able to model the load, and these things are changing those models. Just like residential air conditioner has dramatically changed the behaviors of load, and we've got a research project going right now in which we are helping develop the new models for the new behaviors of these air conditioner systems that cause voltage sag problems. We're predicting some similar issues. We, the team, are predicting some similar issues with the rooftop photovoltaics in affecting the load so that the models don't work. And if you have wrong models, you do wrong things. That's another issue on top of, indeed, having to find a way to get spinning reserve. And by the way, Lloyd or Larry, if I say something wrong here, pop in and correct me. I'm not an electrical engineer, by the way. I'm a nuclear engineer. And you see, when I studied, I never got beyond the nucleus of the atom, so I didn't even do electrons when I was in school. Another issue of some of the renewables, and wind is the poster child here, is the fact that if you look at the typical load profile of how energy is used in California versus how wind typically generates in California, there's not a match. It's mostly generates at night for wind when we need it during the daytime. And this creates a number of problems. The one of them has to do with regulation and load following, because assuming we had a lot of wind on the system, which someday we plan to have, and so if you have a lot of wind in the nighttime and as the morning's coming on and the load starts to pick up because more customers start to use some more, but if your wind is falling off, you now have a double whammy. You have a generation falling off just when the load is picking up. So now there's a much more rapid ramp rate than what we're used to. And again, it's raising some concerns. It's basically costing money. That's what it boils down to, because you're paying for more spinning reserve is right now the bottom line. Yes, is it Gary, I believe?
Yes.
Yeah.
Is this typical only in California, or are there places where this profile is below ground?
Actually, yeah. Actually, I thought California was special, but it turns out this is showing up in other parts of the country too, in which it isn't matching peak all the time anyway. So it's not unique. And as a matter of fact, the next problem I'm going to talk about is minimum load. It's now showing up in a number of places in the United States. I don't know about Hawaii. Terry, is it showing up in Hawaii?
Well, not quite like this, but you do have this disparity between the peak and the wind tends to blow more normally than, or not, but you tend to get the greatest output during the night hours when you have control of demand.
Yeah, Gary, and then Ron.
One reason I asked the question was just because it says California there, but one of the statements made by the Vestas executives when they were here was, well, we can solve the storage problem because the wind is always blowing somewhere. We just got the distribution right. Well, that's true, but it's blowing 12 time zones away somewhere, and that's probably not what you had in mind with the distribution. So that's a very simplistic metaphor that they're using.
Right.
Well,
You're right, and for some things, and again, electrical engineers correct me if I get this wrong, but they're right from the point of view if you make the control area large enough. Then, indeed, things like frequency regulation it can be done. by these long distance because the frequency tends to propagate very fast throughout the system, which, by the way, it used to be believed that it was instantaneous. It's not. As you'll see with some of the technology I'm going to talk about, we can now measure lag and frequency. But it's still considered universal. You correct the frequency here and it immediately corrects over here. But when you get into things like voltage problems and all that, those are local problems, and making the control area bigger doesn't solve the problem. Also, I think markets can behave better in larger control areas. Prediction is better, it smooths out more and things like that. But I don't know, as an individual participant in the market, whether it really helps you or not. But from a market planning point of view, it should help you. So they're partly right. But I think they're partly wrong, too. Another thing you'll hear is that the wind people tend to say, well, gee whiz, if you can handle variable load, then you ought to be able to handle variable supply. The problem is it's a double whammy. Is that when you put variable supply on, you've taken away, in theory, some very consistent dispatchable steady supply. So in a way, it's sort of like increasing the variability of load 2 times. I mean, that, if you get the idea, it's not quite. Yes, Ron? And
Actually, it even gets worse on some islands. There's a study being done at UC Davis on the Galapagos Islands on San Cristobal, and 2 peaks are exactly 12 hours out of phase. They have morning winds
yeah.
Around 6 in the morning, and at 6 at night, everybody comes home and turns on the load. So the wind is even worse in some places than what you're sure.
Oh, okay. And then Teresa, and then you? I didn't get your name, so. Is it Teresa? Is that right? Teresa.
I was wondering if that is a proposed area of research to seek out microclimates where there is more wind in the afternoon. I imagine if you talk about enough sailors and windsurfers, they could probably show you places that there is wind that picks up in the afternoon. Is that something that should be looked at in terms of siting?
Could be. I'm going to say that the wind companies are taking the other approach is let us go to the windiest site and then convince you this isn't a problem. Or we find storage. And as long as there's not a lot of wind in the system, this really isn't a big problem because of the reasons that Carl said. We got ways of balancing it. It does cost money, and CalISO can tell you how much they pay to deal with this, and it's calculable, but it's not outrageous at the moment. But when we get up to 33% penetrations, now it's getting to be a new issue. You had a point?
I'm just curious, we have some research that extends to this, but I was wondering, do you think it'll ever come to the extreme that we may be in a situation where instead of trying to cost our energy to suit our needs, we go along with the industry's needs, and if you want to work in a computer or drive a car, you do that for the hours of wherever that peak.
You're touching on something that, as a matter of fact, I know that Ron and Gaiman are working on a lot, is that, which I haven't talked about, and I won't talk much about here because they're the experts, is you can do things with load to begin to compensate. Now, this is tough to do. To fit this by playing around with load is not easy right now. But there is hope that things with storage associated with them, like the hybrid electric vehicles, et cetera, you get enough of them, you could begin to do some playing some games, so to speak, to begin to correct some of these problems.
It's a challenging system integration problem. Take a plug-in hybrid and get it charged when the wind is blowing. It's not, you know, I mean, when this is how you might do that, but actually doing it.
That's right. It should keep us in research for a long time. Yeah.
This is an i4 problem.
Yes, it is. And I haven't got to the really neat i4 problem. I guess Carl and Terry.
Well, hypothetically, co-siting the solar plant here, if I sited a southwest-facing solar plant, I could create I think I could create a curve that would more resemble the top curve. And one other thing there is the top curve isn't zero base, so
That's right.
there's a little bit of a
There's a load. There's a base load there. Yes, that's correct. And indeed, solar looks real nice. And if you bring more and more solar in, this becomes less important. You don't have to co-locate them, although I think the closer they are, probably the better it is as a general rule, but you don't have to co-locate them. So yeah, there is some other hope here. Terry, did you still have some?
Just to add,
That's what this slide's all about. The other problem that I thought was pretty unique, was going to be unique to California, turns out this is showing up in a number of places, and that is that wind, which at least in California gets preferential treatment, coupled with a whole lot of other must-take type generation for various reasons. Some of them have to do with contracts, some of them have to do with physics. Generally, what happens is that on like springtime nights, the amount of generation available that has to be taken exceeds the load. And as a result, this is when CalISO says they have to find people to pay to take power. And I thought they were kidding the first time I heard that. But it turns out apparently it's true. They have to pay people to take extra power. I don't know why you can't just dump it, but that's, or shut plant. I guess you can't shut some of these plants down. You just can't shut them down. And so as a result, this is a problem to address. I don't know how soon it will go away due to our ability to balance things better in the future, but at the moment it is an economic problem. I'm not sure it's a stability problem yet, but it could be. It could become a problem, yes, if you can't shut things down because you get into over frequency systems in which the frequency gets too high and then you run into reliability problems. So, in summary, transmission must accommodate the supply uncertainty, the ramp problems, the rapid up and down ramp problems, and this overgeneration problem. Now, going on to our third major problem, increasing the power capacity of the existing transmission to handle additional electric power flows. As was pointed out earlier, this isn't strictly due to just renewables. If you build a nuclear power plant or a coal plant out somewhere away from population centers, you're going to run into the same problem. But nonetheless, if we're going to meet the renewable portfolio standards, you have to solve it. You can't avoid it. And so that's what I want to talk about now. The transmission capacity is limited by one, and we've already talked about this one, difficulties with siting or upgrading new transmission. But this problem applies not just to building the new transmission out to the new power plants. It's going to apply when you have to build new transmission to get more power into the LA basin. As a matter of fact, I predict it would be much, much more difficult to build new facilities, new infrastructure in these heavily populated areas than it is out in the areas where it's not as populated. And then there are the thermal limits I mentioned. There are the stability constraints, the voltage, transit, and dynamic stability constraints. And then there's one that I really didn't put on here, but there is the N-1 reliability constraint, which is at the moment considered an acceptable way of running a transmission system. Well, the first I'll talk about is the thermal limit. The transmission capacity is limited by high line temperatures caused by fundamentally I squared R, the toaster effect. And what happens is if you run too much power, the line heats up, it sags into a tree, it causes a short to ground, and it can cause a fire. Those are not good things. The fire is probably obvious. The short to ground can be a major problem. One, it can hurt people, but also it can cause outages. And as a matter of fact, most of the big outages in the world, particularly in the United States anyway, all of them are, the first initiating event is a line sagging into a tree. It happened in 1996, August, in the western United States, and it happened in 2003 in the Northeast system. And so it's not a good thing, and it is an issue. And so we, at the moment, need to limit the amount of current that can throw through these lines. And high temperatures can both damage the line material if it gets hot enough, and so you have to replace the line, or more likely can cause the line to sag too low, and this creates safety hazards and or outages. The transmission capacity is also limited by local instabilities. For example, looking at the LA basin, which is probably going to turn out to be the poster child for problems in California, is that one study done by CITRIS and EPG, the electric power group who happen to live in the LA area, 2/3 of the renewable generation will likely require delivery to the transmission gateways surrounding the Los Angeles basin. This is fundamentally the fact there's load there, and Kirchhoff's law is going to direct most of that generation out in the deserts there and the Tehachapis to the Los Angeles basin. The capacity is limited by voltage and transit instabilities as well as thermal limits. And there's difficulty in upgrading and building these new lines. And so at the moment, this current gateway capacity can only meet 1/3 of the requirements. So by 2020, we'll have to triple the amount of capacity into this area. And there's no easy solution that I see for this problem. And you mentioned earlier about the use of thermal plants. Well, one of the issues, if the fossil thermal plants in the Los Angeles Basin retire because of air or water restrictions, this further increases this transmission gateway capacity problem because of mostly, in this case, the voltage support issue. Well, plus the fact that it'll have to have more demand. I mean, more power has to be gotten in because you're reducing the amount of generation within the area. So this is the poster child of problems that are they're going to show up elsewhere, though, going into San Francisco, going into Sacramento, going into Fresno, et cetera, San Diego. This is another major issue to solve. The inter-area power oscillations severely limited power flows throughout the West. These are big, slow, relatively slow oscillations of power surges, voltage changes, swings that occur across the western United States. My metaphor for it is trying to carry a big, shallow bowl of water, and you walk someplace with it, and it starts to slosh, and so you try to stop it, so you stop, but sometimes it won't stop. It just keeps right on sloshing, and the water sloshes out. Well, a similar kind of thing can happen in which the power can start these oscillations, and they go undamped, and indeed they go haywire. And in this case, this was on August 10th, 1996. This is the actual precursor of the outage where a line touched a tree. It was caused by this oscillation that went on for an hour or two before the line actually overheated and touched the tree. These oscillations are major problems. They cause derating of the certain transmission gateways. And it's derated a lot of our transmission coming into California by thousands of megawatts. And therefore, if we want to export or import, more likely, renewable power, this is going to constrain the amount that we can do. Or you'll have to build extra transmission to make up for the difference. The Northeast, this isn't all due strictly to the oscillations, but they contribute to it. And we're trying to get a better handle on it from research. But that, I believe the thermal limit, is it N-1, Lloyd, is about 7,200 megawatts, and it's running now at about 4,800 megawatts. It's what it's restricted to. And part of it is due to these oscillations. And there's different estimates of how much it is. It's anywhere from a few hundred megawatts to 1,000 plus is blamed on this particular problem. And this happens elsewhere throughout the western United States. And it's also believed by many in the industry, particularly CalISO, that if we add more renewable, variable renewable generation to the mix, these oscillation behaviors would change. Just like a mechanical system, if you go and start changing the weights and the springs and all this stuff, you change the dynamics of the system. This is they think the renewables will change this behavior considerably and make it more unpredictable. So, in summary, and I'm probably running late now. We've had a lot of discussion. To fulfill the renewable integration mission, 1, transmission must achieve 3 broad objectives. 1, provide physical access. 2, accommodate the unique behaviors of renewable generations. And 3, increase the power carrying capacity to handle additional electric flows. For transmission to achieve its 3 objectives at the high levels, like 33%, the traditional build solutions, which is investment in wires and towers and power plants of the traditional kind, I don't think it can do it alone, and there are a number of people in industry who would support that belief. That there are new transmission technologies that at a minimum can make renewable integration easier and perhaps less costly than the traditional go build more lines and power plants. And then these new technologies can endow transmission with improved and new capabilities that would make it easier to integrate these new technologies. So these new renewable generations. So new and expanded transmission capabilities for renewable integration are taken by the 3 main objectives. Provide access is that we need to find new technologies that allow faster siting and also faster approval. And I'll talk a little bit later on more what some of those might be. In the area of accommodation, we need to enhance the behaviors or the capabilities of transmission for power market participation, dynamic behavior, operating coordination of the various power plants in the system, the ramping problem I talked about, and this excess total power and minimum load problems. And then increased capacity, we need to decrease the thermal constraints, decrease the stability constraints, and then plan better for a transmission system expansion than we can today with today's tools. Some of the new technologies provide faster access for new renewables is what I call, in general, putting new transmission lines in a better light. And it's meant to be a pun, because there's two ways to look at this. One of them is that if we can get them out of the light, that is, like bury them, it will probably be much easier to site them. And there are other things, as I'll show in a minute, that you might do to put them in a better light. The other way by putting them in a better light is to make them look better, in the sense of feel better, have higher value. And so there are, matter of fact, we've already done some work on this issue of cost allocation and strategic benefits of transmission that show that the transmission actually has higher value than our current societal due process systems actually come up with. And so that's the other way of putting transmission in a better light. It just says it's worth more than you think it is, and so therefore you're more willing to pay for it, both in terms of economic and environmental costs. Here's some examples of some new emerging technologies, some of which we're already doing research on. Underground transmission, I already mentioned that one. High voltage direct current, advanced transmission line conductors, such as some of the new high temperature low sag conductors that are already now starting to be used. They can perhaps in theory double or triple the amount of current. Engineering compact designs, web-based, those are the ones that put transmission in a different light in how you see them physically. The ones that how you view them from a, I guess, a belief point of view, such things as some web-based interactive stakeholder science tools, which Peer has already paid for the development of one that I think is quite good. The cost allocation strategic benefit analysis tools, of which we've already done some work on. And here's one that's not even a transmission solution. It's such things as distributed renewables and demand response, which would mean you don't have to build transmission at all, to the degree you can put that off. And then new technologies to accommodate the unique behaviors of the renewable generation. And here I think the best way to summarize it, we need a smarter and more flexible grid. Mainly you have more uncertainty, therefore we need something that can respond to that uncertainty faster. And here are some example technologies. Energy storage and intelligent agents to dispatch that storage. Solar and wind forecasting tools, which are already being worked on. Synchrophasor measurement, which is one I was going to talk about if we have time, as the best example of information technology applications in transmission. And then there's power flow control, which is the spatial kind. The storage, by the way, is a temporal control of power flow. But we also would like to be able to control power flow from a geology or geography point of view, which right now the operator is very limited, and Kirchhoff's law rules, and actually a still rule, but some of the research we're doing in spatial power flow control basically changes effectively or essentially the impedance of a line, and therefore changes the power flow. And there's a number of new technologies to allow that through various power electronic systems. And then demand and response, distributed generation, generator and load modeling is a very important area. I don't have time to get into it, but I've already mentioned the load modeling point of view from handling the rooftop photovoltaics issue. Statistical and probabilistic forecasting tools. Brief word on that. Up till recently, the transmission system was planned and operated primarily through deterministic models. The utility was in control and pretty much dictated what could happen and could run these models out and say this is the way it's going to be. The world's changed a lot, and renewables are part of that, and we're going into a world where you need more and more statistical and probabilistic views of the future than deterministic ones, and this is a ripe area for research. And then, yeah.
Just so we can think about this, what's the time constant that the operators are having the most trouble with right now? Is it seconds, tens of seconds, minutes? In terms of intermittency?
Oh, intermittency?
Yeah.
It's probably minutes.
Minutes, okay.
Could be seconds, but from a transmission point, it's probably minutes. But Jim Detmer's Vice President Cal ISO, I think, puts it rather well. He said it used to be the transmission operator had planning tools that allowed them to see into the future, so to speak, and they pretty well knew if they did something, this is the way it behaved. He says that the planning horizon has shrunk to 0. And so basically, operators are operating blind, is the way he puts it. And we've been doing research, particularly in this area, to give the operator now a statistical view of the future. And we just completed development of a tool that's a 24-hour probabilistic, well, it's not truly probabilistic, but at least it forecasts ahead of what, a state estimator, as to what the operator might expect that day. Tells them where the likely pinch points are, where certain lines are likely to be overloaded, and it continually updates that information as the day goes ahead.
That quote's good for dramatic impact, but I think probably there is a lower limit to the timescale, the planning horizon.
I'll show you.
That we really need to practically.
I'll show you. In principle, with phasor measurement units, we can go down into the millisecond range. And we will probably have to at least the second range for automated control. And this is a whole new area of research. The third point was new technologies for increased transmission capacity by optimizing the grid for greater power flow. And here I tried to show, for example, the load areas where most of the renewable generation will be consumed, and then indicate the fact that we have these constraints both from an import-export point of view into California and also import into the load areas. And so what we want to do is remove as many of these constraints as possible so that the existing system, or even if you build new transmission, you get more out of it than what you would today if we didn't tackle these problems. And here are some of the technologies. Dynamic thermal ratings, of which we've already been doing quite a bit of research on. Real-time systems operation, which I'm going to be talking about in a moment. These are based on synchrophasors and their applications. Power flow control, again, energy storage, advanced transmission line conductors, high voltage direct DC, distributed generation, statistical and probabilistic analysis planning tools, and advanced intelligent protection systems, which again we have a major research project going on at Virginia Tech. These are a list of some of the technologies. Okay, now, if you'll bear with me, we're over time. I'd like to talk about the synchrophasor measurement as the heart of a smart transmission system. And because this is where I think most of the information technology new work will come to bear. The phasor measurement unit is a device that is more or less a mature technology today. It's been under development since the late 70s, I guess, early 80s. And it's a device that measures between 30 to 120 times a second the parameters of a transmission at certain locations, wherever you happen to put them. Measures and or calculates voltage and currents and frequencies and things like this. And it also turns out phase angles. And so the heart of it is this piece of electronics. And you put them at various places throughout, in this case, the western United States. And then the one thing that is an important factor to all of this is you timestamp the data through a satellite time signal so that when you take data, you know precisely when that data was taken. And this turns out to be important because what you're going to do is you're going to take this time synchronized data, and let's say, for example, the data was taken at Grand Coulee up in Washington State, and a transmission operator down in San Diego Gas and Electric wants to know the condition going on the grid at that time. Before synchrophasors, there was no way they could tell. Because if they got data from Grand Coulee, because of the delay time it took for that data to get down to where they are, they couldn't know how to compare it to the data they're taking in their local area. And by time stamping it, they can now do that. And they can now calculate measure the phase angle change from, say, Grand Coulee down to San Diego. And this, if you know all the equations that power engineers have to solve, you will know that that is the one of the holy grails is being able to measure phase angle instead of having to guess at it and calculate it through a converging series. And this effectively, well, first of all, you take all this time synchronized data, and then what you do, you have to turn it into useful information, because I'll show you in a minute. It's a humongous amount of information. You need to turn it into useful information, but something that an operator can deal with, because of the speed at which this information comes in and the amount of it, a human being can't handle it very well. And so ultimately the smart grid, I think, is going to be required for maximum renewable deployment in order to have these kinds of response times fast enough to handle a growing uncertainty as we bring in more and more renewables, and markets, load changes, all these things are bringing a great deal of uncertainty into keeping the grid up and running. One way to put this is, if you look at the power system without something like synchrophasor measurements, if you have a disturbance on the power system, you a lot of times don't even know anything happened until it's too late. As a matter of fact, I like to think of these big grid oscillations I was talking about as kind of like swimming with sharks. Say you were going to your favorite beach and you were swimming and you had a lot of friends there, and every once in a while one would disappear, but you didn't know why. Thought maybe they went in the undertow or something. And then you bought a new pair of goggles and you go swimming one day and you find out, oh, I can see, and this whole area is full of sharks. So that's where the people have been disappearing, as sharks. Well, these oscillations actually kind of showed up the same way. Engineers back in the 80s at Bonneville were seeing these oscillations, thought they were seeing them. And they'd go, but the grid's run by models, by the way. Modelers run the grid even still today. So they go to the modelers and say, there are grid oscillations, these big oscillations, and they're dangerous. They cause problems. The modelers would look at their models and say, there's no oscillations. It was like the old map makers, back in the 1400s, 1500s. An explorer would run into an island, go back to Portugal and say, hey, there's an island out there, it's not on your map. And the map makers say, no, it's not there, you were lost. So you need better instrumentation to know that you really found an island. Well, that's where these synchrophasors came in, is that engineers wanted better instrumentation to prove that there was a problem out there. So with synchrophasors, what you now have is an observed event response through measurement-based information systems that allow you to do three fundamental things. One, better system planning. The other one is better systems operation. Then ultimately, the goal is automated control in order to be able to work the system closer to its margins. And so synchrophasor measurements have brought and are bringing to this industry what MRI diagnostics have brought to the medical industry in going from X-rays. It's a very similar kind of quantum leap in ability to monitor and measure what goes on in transmission. But what's even more important, it's wide area. We've had pretty good ability to measure locally pretty fast through regular SCADA systems, but the ability to know what's happening over the horizon has been very limited until this technology came along. Today there are about 60 phasor measurement units out through the western United States. More are being added, not every day, but fairly frequently, and the same pretty much is true of the eastern. The eastern started adding these things big time after their 2003 blackout in August, when NERC came in and said, if you guys had synchrophasor measurements, that blackout wouldn't have occurred. So they've now put in about 100 synchrophasor measurements. And frankly, an IT system is going to be needed to extract full value from these synchrophasor measurements. And let me give you some idea of why. This is some work that Anjan Bose from University of, that's not true, it's Washington State, I'll have to correct that, from Washington State did on data collection from synchrophasor measurements. And here he's looking at doing it at substations. This will vary somewhat depending on where you're doing it. If you look at conventional SCADA data collection rates, the average reliability coordinator has 10 balancing authorities or control centers that he or she has to deal with. The average control center has 100 high voltage substations, and the average substation has 100 measurement points. So the average pulling rate from the traditional measurement system is about, for data, is about every 5 seconds. You get a piece of data. So on average, the data rate from each substation is 20 data points per second. From each control center, or for each control, it's about 2,000 data points per second. So the average data rate for a reliability coordinator is about 20,000 data points per second under the old system. This is where we're heading. Assume that synchrophasor measurements replace all SCADA, which is probably a bit of a gross assumption, but nonetheless for the purposes of putting the magnitude on this. The PU sampling rates are between 30 and 120 times per second. That means the average data rate per sub is about 10,000 data points per second. The average data rate for 100 subs for a balancing area is about 1 million data points per second, and that means that a reliability coordinator is dealing with 10 million data points per second. This is certainly reaching oversaturation from the ability of a human being to handle this. And so now the secret is to develop technologies that allow us to use this stuff. One of the things that we've been involved in helping to develop from the administrative point of view is the real-time dynamics monitoring system of platforms and applications that's been developed mostly by CITRIS, which is the consortium for electric reliability transmission technology solutions, which is run out of Lawrence Berkeley here, but involves a lot of national labs and universities and EPG. RTMDS is composed of a data management hub, a database, web services for reports and data retrieval, and client applications for wide area visualization, dashboards to diagnose the health of the grid, event analysis, and small signal stability. That's those oscillations I was talking about. RTMDS today can do grid stress indications through phasor angle separation. I'll show you an example. Grid robustness through damping status and trend of these low-frequency grid oscillations, and I'll show you one of those in a minute. Also handle dangerous oscillations, frequency instability, voltage instability, and reliability margins. In other words, how close are we operating to the reliability edge? This is kind of a cartoon drawing of what the system may look like. I put this in here so that you can sort of get an IT flavor for what this is all about. But fundamentally a data acquisition system, central data management, and client applications. Two big questions that remain. One is developing these applications, of which we're conducting research in right now, doing quite a bit of that. And the other one is, where do you collect the data and where do you store it? And it's a debate that's going on right now. And Anjan Bose is saying you should do it at substations for automated control and in a central location for sort of planning purposes. Others are saying no, you'll want to do it for central control at a central location like TVA and CalISO. But those are some of the research questions that are going on right now. This is a very ripe area for research. Here's a visualization of the dashboard for the phase angle separation, which gives you some idea of the stress of the grid. And because of time, I won't go into this in detail, but basically it uses a simple red, yellow, and green, and I don't know what the blue color stands for on this, but and there's no red showing up at the moment. If red showed up, it means there's a stress that is too much, and it alerts the operator better look and see what's going on. There's a problem somewhere.
So this is a snapshot of an operator's screen?
Yes. Mm-hmm.
At CalISO?
Yes. Yes. This is now working at CalISO. This technology has been developed about 5 years now. And CalISO now has it on their system, and the reliability coordinators are using it, and it's already been credited with saving a number of potential outages. And we're increasing it all the time. We're adding applications. Yes, Gaiman. Yes. It's real time. And yeah, if you ever watch one of these things, when there's something going on the system, these little things are doing like this. And if they happen to go way over like this, then you panic. Yes, Gaiman.
So what every arrow has 2 degrees. Is that the phase shift between the 2 bubbles that the arrow connects? And why are there 2 numbers?
I don't know. Do you know, Lloyd? He asked what the 2 numbers are.
One of these green flashes has 2
Yeah.
things that look like degrees angles. So what do they mean?
Yeah, I don't know. By the way, the reference is Grand Coulee. That much I know. But I don't know what the 2 different readings are. I apologize. This plot is, it's usually marked. It's a plot of, in this case, it can be anyway. It can be voltage, frequency, and I'm not sure what this is. I can't read it. It's too blurry. But it's usually at one of these points, and the operator picks it.
I'm thinking of what the two numbers are.
It's what?
The degrees are pretty close together,
Yeah.
so you need the minutes reading. And then it gets
Oh.
in other words, a fraction of a degree.
And then presumably
I don't know.
phase shift translates into power flow in one direction or the other, right?
Right, power flows from higher angle to lower angle.
And how elastic is that? Is it 1 minute? How do you convert 1 minute shift into how many megawatts?
Well, they do it internally by just knowing what they measure the power flow on the line. But the phasor is an actual measurement of the phase angle from one bus to another. So you don't have to compute anything, you just sort of have it. You can use the phase angles then to compute other things. But I think it's mainly by experience that the operators know what is the acceptable angle between buses and across the system and what isn't. Well, you know if it's
Yeah.
more than 90 degrees, something went out of phase, something's moving forward.
But I thought that it was actually used in Europe. I once went
Yes.
to visit such. It's used to, for example, dissipate power. That it's used to ship power from southern Europe to northern Europe and dissipate some of it in transmission lines.
Yeah, what
Yeah.
you have to do is you have to control generators and actually increase or decrease the excitation controls on the generators and have a certain generator put out more power, increase the phase angle at its bus to send the power down to a load somewhere else. It's very tricky to do, but the operators can do it. If you have to do it by completely.
Right. And some of the research we're heading towards is to be able to use such things as pattern recognition to begin to tell what the problem is causing this. We're now funding some research on grid oscillations to begin to do that. It's using algorithm development instead of pattern recognition. But anyway, there are people in the industry who've worked with this for the last 6, 7, 8 years who can do it. Barat, what's his last name? Bergava at Southern California Edison is amazing. He can sit and watch these real screens and tell you this power plant over here is acting up, and so the guy, it's all in his head. But someday we've got to get a computer that can do that. Yeah, Gaiman.
Is there a time period between when a data sample is taken to the point where it was, by the time it reaches to sometime in the future, it's too late to do anything about it? Meaning, how fast can operators respond before it's
You've raised a whole bunch of issues. One of them is how fast can you take the data? 2, how fast can you communicate it? There's obviously a lag time from, say, measurement in Grand Coulee down to San Diego. It's in the millisecond range or second range. I don't remember. It's pretty fast, though. And then you've got the issue, how fast can an operator operate something? And that's probably at best right now in minutes, and they don't even usually operate that fast. There are automatic protection schemes called RASs that will operate automatically under certain conditions. Right now, those aren't tied into phasor measurements that I know of. I think Southern Cal plans to tie some of those into phasors in the next year or so. And as a matter of fact, some of the research we're working on is right now, these protection systems protect a local thing. Yet they can cause a widespread outage. By protecting something locally, it actually can sacrifice the whole organism, so to speak. I call that the autoimmune disease. We are funding research right now that will use phasor measurements to begin to be able to predict. If you take a protection action here, what will it do over here, and what can you do to optimize your protection system to maximize the reliability of the system? Yes?
Two questions. One is, how much is one of these phasor measurements to cost? And the other is, what are the control points? You mentioned excitation voltage on the generator. What are the other kinds of control points that you're going to use this information on?
Right now, you've got generators and you've got load. And load pretty much right now, until we get demand response in place, is pretty much you just shut people down or you lower voltage. And in generation, it's changing these excitations. There are new technologies coming out like fax devices and smart wire systems, maybe storage, which gives you a temporal. But those technologies are coming into place. DC, AC, DC systems, all these will in the future, we believe, give the operator more control ability. But at the moment, they have a limited ability. So I like to think our research program is balanced in that we're doing the research to give a decision support system to the operator and to the system if it's automated. But down the road, we've got to have the physical ability to actually do something about it. And today, that's limited. And we're working on technologies, the whole industry, the whole world, is working on technologies to bring that about. Right now, in some cases, they're free, so to speak. When you buy a Schweitzer relay, they're putting them in there as just putting them in. Obviously, you probably pay for it somewhere, but it's not obvious. But those haven't been certified as real-life phasor measurement units yet. If they ever are, overnight, we'll have thousands of them out there. But right now, I'm going to guess it's, what, 10,000? Larry, you looked at putting some more down in San Diego.
Yeah, they're about 20,000 pieces. Most of the cost isn't actually purchasing the unit, it's the installation,
Yes.
the communication system.
Yes, exactly. It's the IT part that actually is the expensive part on these things.
The limiting factor is not the cost of the box by any means.
Right.
So if you can imagine having a 1,000-fold increase in the units, the problem is what are you going to pay?
Exactly. It's the application, the ability to transmit the data, store it, utilize it, get information out of it. Then the next step is what can the operator do about it? Because at the moment, when they see an oscillation, all they can do is hold their breath and start cutting back on imports as fast as they can so they don't get another major cascading blackout. But yes, you're right. And that's why I wanted to bring this to your attention, because this is about information technology. And let me just hurry on, please. The online damping monitor system, this is another tool that's been brought to the system that still we're developing, but this again is the famous one in August that caused the outage in the western United States. This is an example of, and I'll show you an actual display, but this particular tool can calculate, one, the frequency of a particular oscillation and show you the damping ratio and show you how it changes over time. And let's see what's in here. Well, okay, this is an actual example of a screenshot, and you can see some of them on here and how they're progressing. And when they get to the yellow line, okay, the red line is an alarm threshold that tells the operator you're now in dangerous territory. The yellow obviously says start watching, the damping's getting too low. And so a poorly damped mode would be this one, and this is one the operator is going to want to watch real closely. Where we're going with research right now at Pacific Northwest National Lab, they're developing some tools that will, one, be able to more rapidly detect these oscillations than they do right now. And then what really we're hoping they can do is they'll be able to tell what is causing the oscillation, which power plants are fighting with one another causing the oscillation, so that the operator might actually do something about it with knowledge, as opposed to at the moment they're guessing. And at the moment they generally just back off imports and things like that. They don't dare start playing around with these power plants as a rule. This is an example of the display. Here again was this one I showed you a close-up. There's one that is a waterfall, they call it display, that gives you some history of what's been going on with the low-frequency oscillations. There are two of them, I believe, shown there. And then here's one that shows a different kind of meter system that can show you somewhat how these oscillations are changing, if they are. And it has built into it the same system of warning into it, and I don't know why the differences are there. And by the way, this is undergoing evolution all the time. CITRIS is continuing updating, and these pictures are about 2 years old right now, and I haven't got it, or maybe a year old. I don't have any modern ones. But this gives you some idea of what can be done. And like any of these systems, the operator can change them and come up with different things. I guess I was explaining what all those were. So this is the last slide. Some other IT aspects of transmission operation that can spring from this. One of them is expand the situation awareness to automated control, to intelligent protection, and decision support, operation, and maintenance. I personally believe that we're going to get to the stage that the electric system will be operated like a thermal mechanical system, in which the operator is the one who would determine when something is taken out for maintenance, when it's going to have to be done. Today, those are not that coordinated. But I think down the road we'll have the technology to be able to know this transformer is getting ready to go. You got 3 months with a 95% confidence ability. The operator will have to make a decision. Do I take it out now, fix it now, or do I gamble for 3 more months because I need that transformer working right now? I think that's where we're heading with this kind of data. We want to be able to integrate the operator intelligence with physical system action. We've already talked about that. We need to give the operator more physical things to do with power flow control, storage, restoration. If there's an outage, how do you bring the system back up faster? Islanding is another thing that's being looked at, particularly Arizona State's doing quite a bit of research in that area. And then we can think about expanding system security as we worry more and more about security issues from cyber threats and from physical threats. Thank you. So.